co-director of the Green Design Institute, member of the National Academy of Engineering, distinguished member of the American Society of Civil Engineers, and given that there's those two distinctions, there's actually a long list that goes with it. So we're very fortunate to have somebody as distinguished as Dr. Hendrickson here, and he's going to talk about electric vehicles. Okay. So again, thanks for coming, and Dr. Hendrickson, for you.
Can you hear me in the back? Okay. It's a lot of fun to come back here to Seattle. I grew up in Seattle. They took me to the University of Washington Club overlooking the stadium, and behind the stadium was the bay that I can remember water skiing in several decades ago before they lowered the speed limit out there. So it took me back to when I was much younger. So today I'm going to talk about electric vehicles and life cycle effects, and I thought I'd do one little commercial. We have a Carnegie Mellon Vehicle Electrification Group on campus, and that is an interdisciplinary group that draws from robotics, from electrical engineering, from material science, from mechanical engineering, and from civil engineering. So it's a whole group of us that got interested in electric vehicles. And there's all sorts of different aspects that they work on, from look-ahead software to supercapacitor battery combinations and that type of thing. So I'm going to be talking about a little bit of that work today. What I'm also going to be doing is kind of giving you a little bit of a history, because I got involved in electric vehicles back in the early 1990s. So I'm going to tell the story of that involvement back then. The other group that's acknowledged up here is Green Design Institute. I've been the co-director of the Green Design Institute for quite a while. We got into the business of doing pollution prevention and life cycle assessment studies, and that work on electric vehicles in the 1990s was the first time I did a life cycle assessment study. So it's a good story for that reason too. Green design draws from the business school, from engineering, and from fine arts, and from science. So we kind of cover the gamut. I put up that I'm et. You'll soon find out why I'm et in this story. But I should have my thanks to my colleagues that I'm going to draw that we've done joint work on. Lester Lave, who's an economist in the business school, Fran McMichael, who's a environmental engineer, Jeremy Michalik, who's a mechanical engineer, and then two doctoral students, Norman Shaw and Elizabeth Trout. I'll talk a little bit about their work. So with that, so what I'm going to be talking about are electric vehicles, and just to be clear, you have a number of combinations of vehicles that run on gasoline, actually gasoline and ethanol these days. Most of the gasoline that we're burning right now has a fraction of ethanol in it, or electricity that's coming from the power grid. And you have conventional vehicles, the kind I'm used to driving around in. You have hybrid electric vehicles, which still run on gasoline, but the actual drive for the motor is electric. You have plug-in hybrid electric vehicles, which can run on either gasoline or on electricity. And then you have battery electric vehicles, which have larger battery packs that run strictly off the power grid. One of the things that goes on with electric vehicles is there's all sorts of different flavors of nomenclature. So nowadays, BEV that I have up there as battery electric vehicles are also called AEVs for all electric vehicles. And some people use PEV to stand for both the, what I have up there, plug-in hybrid electric vehicles and for battery electric vehicles. So I'm going to stick with this nomenclature, but if you read press reports or read government reports, you're just going to have to be flexible about understanding the different types of notation that people use. And I said I'd talk a little bit about history. Well, this is history for electric vehicles. The caption down here says, Thomas Edison poses alongside the Bailey Roadster that survived a 1,000-mile run. And this is clearly in the early part of the 20th century. At that time, electric vehicles were very much competing with gasoline-powered vehicles for the dominant technology. Thomas Edison was really smart. He invented the electric light. He put in the first power grid and the first power generation. And what he was looking for was to make money from vertical integration. Okay, so he was going to provide power, and at the same time as providing power, he was looking to try and stimulate demand for that power at the same time, hence the electric light bulb, and hence electric vehicles like this one. And of course, you notice new Edison storage battery on the sign. He was not only making money from generating the electricity from selling the electric light bulbs, but also from selling his electric batteries in this whole vertical integration. That didn't work out, of course, so the gasoline vehicles became the dominant vehicle that I grew up with, certainly. But more recently, there's been increased interest in electric vehicles of one kind or another. And this is just an example of some of the vehicles that are for sale right now. There's a plug-in Prius, which has a 4.4 kilowatt hours nominal battery size, 3.2 kilowatt hours usable, and has an all-electric range of 11 miles. By the way, one thing you know from that nominal versus usable is that there are different control algorithms that are used for charging up the battery. The manufacturers don't want you to charge too far, don't want you to discharge too far, and so they have controls on how far that swing is. And if you look at the different nominal versus usable for the different companies down the vertical column there, you'll see that different companies have different philosophies about what to do with that regard. And that's one of the things I'll talk about as a research question at the end. You have battery electric vehicles, you have plug-in hybrid electric vehicles up there. The Tesla has a range of 265 miles, and then it ranges down to the Prius. Anytime you see a range like that for an electric vehicle, say to yourself, that is an uncertain number. It's going to be uncertain depending on what the battery temperature is. It's going to be uncertain whether or not you're running the heater, whether you're running the entertainment system, how you're driving. All of those things will affect your range. And okay, let me jump forward from Edison to the early 1990s. And at that time, there were regulations in place in California that were requiring the sale of what they called zero-emission vehicles. So I'm sitting around my office one afternoon with my colleagues Lester Lave and Fran McMichael, and we asked the question, are these really zero-emission vehicles? And so that's how I first got involved in looking at electric vehicles. So just to give you the chronology, January 1993, we wrote a proposal and we're given a grant from the IBM for product design for the environment to the Green Design Initiative at Carnegie Mellon. And what we were doing for IBM was kind of looking at the energy efficiency of computers, end-of-life treatment for computers, recycling computers, waste management for computers, those sorts of things. And as a result, Lave, Hendrickson, and McMichael, or Lave, L, et al., that's why I'm et, I'm the middle of the alphabetical sequence. We started working together and started thinking about life cycle product impacts. And one of the things we thought about was whether or not electric vehicles are really zero emission. And so we wrote up a manuscript and sent it to Science magazine for review in November 1994. It was accepted in Science in March of 95. I told you I'd give you a history. Just to give you the context for this paper that appeared May 1995, California and a number of New England states following California were requiring 2% of vehicles sold to be zero-emission vehicles, ZEV, by the year 1998, so 3 years in the future from where we were at that point. And then 10% by 2003. Okay? And the goal of this requirement was to improve urban air quality. So they were concerned about the conventional air emissions from gasoline-powered conventional vehicles. In response to this mandate, General Motors did quite a bit of research and developed the lead-acid battery-powered EV1 as a zero-emission vehicle under the regulations in California. The point of our little science article was to say that the life cycle emissions of lead associated with these lead-acid batteries due to manufacture, and we estimated a 4% release rate to the environment manufacturing lead-acid batteries, and recycle of the batteries, and we estimated about a 2% discharge in the environment from recycling the batteries. And we thought that this was going to be a substantial amount of lead going out into the environment. And we based that basically on the best data we could get, which was U.S. Geological Survey data, Toxics Release Inventory Survey data. We couldn't get direct data from people like EPA because every lead recycler and manufacturer in the country was under a legal case at the time. So it was all locked up. So the science article came out. New York Times got a hold of it and published a story about our analysis on the front page on the 19th of May, 1995. This is the EV1. Any of you seen an EV1 or driven in an EV1? I didn't think so. They were mainly in California, so it doesn't surprise me. If you look over the sorts of things that were in this, they had a big lead-acid battery pack, but they had a lot of stuff that has been introduced into regular motor vehicles since 1995. They had things like aluminum space frame. They had keypad entry. They had airbags, high technology solar glass, regenerative braking with a drive motor. First time General Motors did that sort of technology in a production vehicle. Lots and lots of technologies were developed for this that have appeared in subsequent vehicles. This was our model. This is the simplest model you could think of for analyzing kind of lead emissions to the environment. It was 5 factors. A is watt hours per kilometer, so how many watts you need to drive a kilometer. B was the kilograms of lead per kilogram of battery, kind of the fraction of a battery that was lead. C was our environmental management term, how much lead got out into the environment versus the lead used in the battery. D is the watt hours per kilogram of battery per cycle, so it's a battery technology sort of thing. And then E is the lifetime. It's the number of battery cycles that could be undertaken over the course of a battery lifetime before you had to replace it. So the lead release per vehicle kilometer then was A times B times C divided by D times E. Pretty simple little model that we put together. Just to give you an idea of an example calculation, we did it all with ranges, but 167 watt hours per kilometer, 70% of a battery weight was lead, 2% released to the environment over the life cycle, and I showed you higher numbers in the last slide back there. 40 watt hours per kilogram of battery, 1,100 cycles per battery lifetime. By the way, the EV1 claimed only 550, half that. That meant that the lead release per kilometer for the EV1 was something on the order of 50 milligrams of lead per kilometer. Well, I remember when we had lead additives in gasoline. And so this is comparable to when we had lead additives in gasoline. So I have a car with 25 miles per gallon, and I use 1972 leaded gasoline. The car is releasing about the same amount of lead per kilometer. If you had a much more efficient car, 45 miles per gallon, of course, you're going to drop below that. Okay. So our basic argument was getting the lead out of lead additive gasoline really led to many public health benefits. And so this was a step backward to start introducing a technology that would have comparable lead emissions to the environment over the lead life cycle of the vehicle. So we were arguing that this is not a zero emissions vehicle. You really want to think about it over the life cycle. And over the life cycle, you got this problem with manufacturing and recycling the batteries. This is kind of partly a story in kind of technology and partly a story in academic research. Okay, we were these three academic researchers who put out this article in Science that got picked up by the New York Times, and turmoil then ensued. Okay, so Lester, Fran, and I kind of dropped what we were doing for the next 2-3 days. We were manning phones simultaneously on many occasions with people calling in and asking what the heck we were doing. Lester didn't trust us to deal effectively with the press, so the first thing he did was sit down and write up talking points. And these were the things that we wanted to get across about our message to the public. If any of you get called up and said, gee, by a reporter and say, gee, I'd like to interview about your research or, whatever, subject X, sit down beforehand and write up a few talking points. It's really a very good practice. And make sure you get them out during the interview with the person. Science published 8 comment letters on our study. The comment letters were longer than the original article. And the comment letters came in from David Allen, who is a chemical engineer on the faculty at University of Texas at Austin, Robert Stempel, CEO of GM, the Electric Power Research Institute, Argonne National Laboratory, the Union of Concerned Scientists, Dan Sperling, who's up at University of California, Davis, Robert Sokolow from Princeton. Okay, so lots and lots of comments. By the way, they published 8 comment letters. They got a bunch more. We saw the bunch more, and we're really sorry some of the crazy off-the-wall letters that we saw didn't make it in. They put in kind of the responsible ones. We got letters from CARB. We had a visit from the battery manufacturers to come and talk to us. And of course, we're all a bunch of researchers and academics, so there was a bunch of follow-up papers that were prepared. And we were roundly criticized, and I clumped the various critic camps into 3 different areas. Lester, Hendrickson, and McMichael are dumb, misinformed, do science for sale. It turns out that General Motors had given some grant to the university, and so we were tainted in terms of our resources by that grant to somebody in another college. Have bad motives, make mistakes in high school chemistry. Fran just went crazy when somebody criticized him on making high school chemistry mistakes. So that was one camp. Second camp, Leave, Hendrickson, and McMichael may have a point about lead, but lead-acid batteries are interim, and electric vehicles are just good for the environment, and so we should be encouraging them. And then the final camp was, I think, more in agreement with us. Leave, Hendrickson, and McMichael's application of life cycle systems thinking may be worthwhile. Let's work together to evaluate the benefits and the costs of electric vehicles. So those are the different critics. And we also had all sorts of disagreements. We based our kind of mid-range estimates for how much lead was going to come out based on as I said, the USGS and TRI data, and then basically on how the EV1 was performing, because that was the one car we could point to that had things. Energy density, the critics thought that we were going to get much better lead-acid batteries. The driving range, we were basing it on what people were actually experiencing. GM claimed you could get a little bit better, but again, you run the heater, you don't drive as efficiently as you can, and you're not going to see that sort of range. 200 plus was what the critics were saying to us. Energy required, the GM EV1 was 140 minimum they published, but we were using what was actually being experienced. And the critics said, oh no, we're going to get much more efficient, very, very rapidly. The battery mass, that wasn't that much of a difference. And of course, the battery type, the critics thought that very quickly there would be benign battery types available for electric vehicles. So those were the kind of the performance factor differences, you know, a factor of 2 or 3. These are the strongest disagreements. Only lead released locally and directly to the air is a health concern. So it doesn't matter where lead might go into the water supply or ground or anything like that. It's only air that you've got to worry about, and it's only local. Lead can be processed and recycled so that less than 0.001% is released to the environment. That was what the battery people came and told us, and I still don't believe it, but anyway. Lead releases are only to be avoided if direct health effects can be shown. So don't worry about lead getting out in the environment unless you can prove that there are public health effects. And then the one that I'm still not sure about, zero emission vehicles aren't responsible for power generation emissions. Okay, so the idea is that the only thing that matters if you're driving a zero emission vehicle is tailpipe emissions. It doesn't matter that you're taking electricity that's generated by some coal-fired plant somewhere. And I don't know, you still see the same language. There's a competition going on for zero emission vehicles for the snow. And I keep thinking to myself, where do they get electricity up in Alaska? And I think to myself, it's a lot of diesel generation. So we had eight letters that came into Science, and we did a reply. This is the first kind of paragraph in our reply. Reaction has been astonishing in terms of the level of attention, venom, and desire to defend electric vehicles. We emphasize 4 points. Environmental problems are complicated and life cycle impact should be analyzed. We're really intent on trying to change the mindset from just worrying about tailpipe emissions to worrying about the whole systematic life cycle effects that might be coming about because of this change. We used the best data available and included wide ranges of data. We examined technologies for 1998 vehicles, that is, the vehicles that were mandated to be sold in 1998, not proposed or hoped for technologies. And, of course, we examined total emissions of lead, not just air emissions. And one argument that we got was that this was an example of technology forcing. That by putting this mandate in place, the motor vehicle manufacturers would then be incentivized to change the sort of battery technology that occurred. And this is our reply to that. The 1998 mandate means that automobile and battery manufacturers must spend hundreds of millions of dollars on current battery technology. These batteries would require up to 1,000 pounds of toxic metals in each electric vehicle. Heroic efforts would be required to smelt and recycle these metals without significant environmental discharge. Research and development should focus on promising technologies that do not require large quantities of toxic materials. And that's pretty much our kind of pollution prevention philosophy. Avoid toxic materials whenever you can. One follow-up paper I just wanted to mention. We did an analysis using kind of conventional air emission models, right? That's and looked at kind of a major increase in the motor vehicle fleet to be electric vehicles. And we found that there wasn't going to be much in the way of ozone benefits. And the reason is, of course, the electric vehicles were going to be drawing power from the power grid, and the power grid had a number of emissions in the different locations they would be. And Lester had this nice quote in the follow-up article in the New York Times: the new car is no longer much of the smog problem, and therefore can't be much of the solution. I've given you enough on this. Suppose the government were to require families to purchase 1,000 pounds of a highly toxic substance, cause all sorts of chronic illnesses. This toxic substance is being introduced in order to lower exposure to a much less toxic substance by a tiny amount, that's ozone. An amount too small to be measured reliably. Does the government's requirement make sense? So, okay, what happened? Let me start picking this up a little bit and moving on. The zero emission vehicle sales mandate was delayed. Still kept on the books, but the timeline for when zero emission vehicles were required started moving out into the future. General Motors discontinued production of the EV1. It turns out they hadn't sold any. They just had leased vehicles, and so they recalled all the leases. Lester, myself, and Fran were accused of killing the electric car. I'm so glad. It was just in the book who killed the electric car. We didn't get into the movie. Anybody seen the movie? Yeah, we're not in there, thank goodness. And I've already said this, considerable EV1 technology, and I think it was really good and useful technology, resurfaced in hybrid electric vehicles. I threw this in. This is the American metal markets. They're the people who kind of follow metal markets in the United States and in the world. This was the Metal Statistics 1996 review of the lead market. And they started off with, during 1995, there were a few major events that affected the lead market in one way or another. In May, 3 professors from Carnegie Mellon University issued a report, which appeared in the New York Times. They had this timing backwards, entitled Environmental Implications of Electric Cars. And we disparaged the use of lead acid. And that, they went on to say, we've been refuted by everybody, but I'll still stand by our analysis. Okay, let's move on from 1995. And actually, some really positive things have happened since 1995 in the realm of electric vehicles. The most important one is new battery chemistry. And in particular, we suddenly have a number of new battery chemistries that are being used. Nickel cadmium was one of the first to appear, but then there are a number of different lithium chemistries that are appearing in production vehicles. And of course, the lithium batteries have fewer toxicity issues relative to a lead acid battery. I say this is really a positive thing, but standing here in Seattle, I should note that there are some problems with the lithium batteries. There's a little problem with the Boeing Dreamliner right at the moment, in that the batteries seem to be wearing out quickly and we're overheating, and so now the Dreamliner fleet is grounded. Oh, the New York Times article. Anybody been following the New York Times article lately? This appeared February 8th. One of the reporters for the New York Times borrowed a Tesla vehicle and wanted to test drive it along the eastern seaboard of the United States. He happened to borrow the car on one of the coldest days of the year. In fact, I think it might have been the coldest day of the year. And he was driving along, and it failed to make it to the next charging station in the Tesla network. And since the 8th of February, when the article has appeared, there's just been this back and forth between Tesla and the reporter about how he drove and what he was doing and did he charge the battery correctly and all of this sort of thing. And all the Tesla owners have been criticizing him because he didn't do things the way they would have done it. But I think one of the take-home messages is that unless you're pretty careful about how you're dealing things, you may run into these sorts of problems. And this was, of course, the Tesla vehicle being towed into the charging station. Feel sympathetic for the reporter somewhat time. New motivations. There's new technology, and there's also new motivations for electric vehicles. First, there's energy security concerns. There's a growing awareness that importing lots of petroleum has major problems for the United States, and there's quite a bit of interest in trying to move away from imported petroleum just for having better energy security. We've had higher petroleum prices, and basically that's driven petroleum out of the power generation market at this point in time. Things like natural gas have been growing and some renewables have been growing. Climate change concerns. The original zero emission vehicle mandate in California didn't say anything about climate change. But of course now we're starting to become much more sensitive to the emission of greenhouse gas emissions. And of course, one of the things that you'd like is to be able to reduce that. And there aren't very many effective technologies for reducing carbon dioxide emissions from the tailpipe of a motor vehicle, other than going to another kind of fuel. Improved information technology for vehicle control. It's playing a significant role. It's better control of how the vehicle performs and how the battery is managed. We've seen some progress towards cleaner power generation. You see that here in Washington State. Somebody was telling me about wind farms that have been put in place. And of course, there's the traditional hydropower out here. Pennsylvania still has a much higher reliance on coal-fired power plants. There are new subsidies for vehicle electrification. So if you fill out your taxes, you'll see that there are checks to see whether you bought a energy-efficient vehicle. There are optimization models for vehicle design. They're a lot more sophisticated than they were back in the 1990s. I already gave you a slide with the multiple different types of vehicles. Back in the 1990s, there were only a couple. Now we're seeing a wider range. And the other thing that is appearing is more investments in charging stations. Anybody know the nearest charging station to where we're sitting right now? Yeah, it's about 20 meters that way. I walked by it today. So you're seeing more and more of that. I showed you that slide. And I've talked about kind of all these positive developments. Thing to ask is how much can battery-powered electric vehicles help? First thing, they offset gasoline use directly. Very little of our power generation is coming from petroleum these days. They changed the emission profile. You have fewer emissions associated with gasoline production and combustion, so refinery emissions are reduced. You have more emissions associated with battery and electricity production. And battery production is something that's been focused very much on trying to improve the performance of batteries. And we'll probably see a wave of reducing kind of the environmental impacts associated with batteries, the new battery chemistries coming up here. The electric vehicles change the location of emissions. That doesn't matter so much for greenhouse gas emissions, but it sure does for air pollution that's released in urban areas, because the exposure to conventional air pollutants is going to vary. One kind of negative thing about all electric vehicles is you've got to carry batteries around with lower energy density than petroleum. And that's why you see the smaller range, because you have all this penalty of carrying around the weight associated with the batteries compared to high energy petroleum. Unless the infrastructure is altered, I say down there. If there's some way of getting energy out of the vehicle by induction or something like that, you can see a change. So what's going to happen with electric vehicles? I got to admit, I'm kind of unsure. I am completely unsure. It really depends on how things are going to play out. And I thank Jeremy. This is a paper that Jeremy took the lead on, trying to estimate the lifetime costs and emissions damages for different kinds of vehicles. It appeared 2 years ago now. You can see his base case, the net present value of lifetime costs, the conventional vehicle and the hybrid electric vehicle and the plug-in hybrid with a range of 20 kilometers, if I recall correctly, are about the same for his base case. And the larger plug-in hybrid with a 60 kilometer range and the battery electric has a much higher cost overall. And the real difference there, there's some savings on gasoline with the more electric vehicles, but the vehicle cost itself starts to go up. So you're trading off kind of lifetime savings in gasoline versus higher capital costs. Then, if you kind of think that electricity prices are going to be dropping over time and that we're able to shift to more renewable power, you can see a change. The conventional vehicle starts to look more expensive than the electric vehicles. And in the other case is that if you think that electric power is going to start going up and gasoline prices don't start racketing up, and you think it's going to be difficult to switch over to renewable power, then you got the opposite scenario. The conventional vehicle comes out as the winner. And frankly, I don't have a good probability set for which scenario we're going to see. I think almost any of them could be equally likely. And so I'm not sure how this competition, first between conventional vehicles and hybrid electrics, and then secondly between all battery electric vehicles and then plug-in hybrids of different ranges is going to play out. And we're going to see how that happens in both the marketplace over the next few years and in the kind of public policy arena in terms of what is subsidized and what is pushed. Certainly, right at the moment, the battery vehicles, the electric vehicles, have only a very small share of new vehicle sales, despite the fact that there are a number on offer to the public. It's less than 1% are coming out as electric vehicles. And of course, I talked about all the promising things that are happening and the things that are helping electric vehicles. There are also a number of barriers, and I thought I should say a couple of things about that. You need both chargers and electric vehicles, so you got to have them both coming together. And if you have one or the other, it's a chicken and egg problem. It's not going to work. You got to have the charger and the electric vehicle. Range anxiety and/or charging time. Okay, if I can only go so far in a battery electric vehicle, I have some anxiety about whether I'm going to make it to my destination. If I have a charging station, I can stop and charge up, but then of course I've got to wait for the charging to occur. And of course there's fast charging, and that may have impacts on the battery degradation. Electric grid limitations so far has proven not to be an issue. If we see major switchovers to electric vehicles, this may be more of a concern. We're doing some more work on how many residences have both parking, dedicated parking, and charging infrastructure available. If you look at vehicles, we find that about 50% of vehicles have dedicated parking at home, and 30% have both parking and charging. So that's kind of limiting what the market is for electric vehicles. If you look at it on a household basis, the numbers are higher, so a household can have one electric vehicle. But guess what? More more than 50% of households have more than one vehicle now. So you got to have multiple spots if you're going to charge overnight. So a couple of conclusions I do draw. I think it's clear that right now that smaller plug-in hybrids are advantageous. That's because the batteries, as you pile in more, have a penalty both on the manufacturer side and the cost side. And so I think if I was a motor vehicle manufacturer, I'd be targeting the kind of the short range market. And it turns out in the United States, there's a lot of people who don't drive very far on a daily basis. President Obama has put forward a goal of a million plug-in hybrid electric vehicles by 2015. I think that would be a lot more achievable if we focused on the small battery packs and made the vehicles a lot cheaper than if there's a large battery pack. Lots of things are going to happen with regard to battery cost and performance, and how that plays out is one of the critical factors in which of those scenarios I was talking. New chemistry battery costs, that's the lithium batteries, should be declining as they become more familiar, the technology improves, that type of thing. Degradation models for batteries, we still don't have firm understanding about what's going to be the degradation phenomena under different charging regimes and under different operating conditions. The motor vehicle companies are starting to get that information, but I don't think they're optimal yet. And then optimal operation algorithms, look-ahead sorts of things, combinations of supercapacitors and batteries are new technologies that may change things. So charging infrastructure is important. Targeting, I think, short-distance travelers. Funny thing is that when you run simulations on carbon dioxide prices, you got to get up to a pretty high carbon tax before you can tip the balance from conventional hybrid electric vehicles to plug-in hybrid electric vehicles. One of the things that's going to be a motivator for the motor vehicle companies is they get some good credits for the electric vehicles under the new CAFE standards that have come in. So you're going to be seeing them probably subsidizing the cost of the purchase of electric vehicles. Oh, I started off this talk with, gee, what's a zero-emission vehicle? And this is my answer. Those of you who bike or walk, this is a lot closer to zero emissions than even an electric vehicle. But of course, even here, you got to say to yourself, okay, you've got to manufacture the bike. Maybe instead of fancy composites, we can get by with bamboo bikes or something like this. And of course, there's some people who argue that people who go out and exercise burn more food, but that's probably not that relevant. I just thought I'd mention I have owned an electric vehicle. I don't own an electric vehicle anymore. This was the electric vehicle that I own. This is my youngest son, Peter. He drove it around the neighborhood. It was a lead-acid battery powered electric vehicle, and yeah, I took measurements just to find out how efficient it was. He really liked it. Oh, we gave it away to friends who had younger kids. Okay, conclusions. One thing that I hope I gave you the impression is that you sit in your offices and you're doing kind of academic research and you wonder whether it ever has an impact. I can tell you, you can have an impact. One of the stories of that 1994 paper is that it really had an impact on what was playing out in the motor vehicle market, the lead market, and in public policy. Vehicle debate advanced from focus on just tailpipe emissions to life cycle issues. So when I was talking about EV and where we are right now, I tried to talk about life cycle costs. I still think, and Fran and Lester agree with me, that the 1998 zero emissions vehicle mandate was premature. Big change that's happening is that new battery chemistries give us some real promise for making changes in the electric vehicle performance. By the way, I should mention that lead emissions, I still think are an issue because we still have a lot of lead acid batteries that are being hauled around as starting batteries for all the conventional vehicles and a lot of the hybrid electric vehicles. So they're still there, and we should try and improve the environmental management in the manufacture and recycle of those lead acid batteries. If anybody's interested, you can look at papers. There's the original science paper. There's the one I talked about for ozone reduction versus lead. And then a couple of more recent papers on kind of optimal design and life cycle analysis for electric vehicles. I'll stop there and entertain questions and see if anybody wants to talk. Yeah. Michelek and Company.
Referring to the 2011 Michelek paper, it seems odd to express the emissions as a monetary value. Can you comment on his methods there, or I guess I guess just comment on his methods, because it doesn't seem to be a fundamentally dollar-related phenomenon.
The basis of that are essentially tracing out public health costs associated with the fate and transport of emissions. So that's what's behind all that. And there's a whole literature on that topic for trying to come up with it. I would say the numbers are fairly uncertain. In particular, the geographic information you got to have is pretty specific, because what sort of public health costs you're going to have is going to be dependent on who gets exposed to that emission. So this is kind of an average over the country that they were using. But that sort of calculation for monitorizing a conventional air emission, there's considerable literature on it. And I think it's uncertain, but it's kind of helpful to try and get some comparable numbers like that. And certainly for kind of the public health costs of asthma and that sort of thing, you have some basis for the value of life. You're just using kind of ranges, essentially, to come up with numbers like that. But there's one model, for example, there's an NRC study called the External Costs of Power Generation, and they did the same sort of thing, only they did it using a model that was county specific. And so they had power plants located in different counties, and they came up with monetary costs based on the public health costs that they would expect from those emissions. Yeah.
Does it work? Okay. In your slide that shows 3 scenarios of costs. If you could go back to that one, yes. I would like to get a little bit of help on the worst scenario on the right side in explaining the very large chunk of emission cost for battery electrical vehicles in comparison to others.
Okay, this would be if we do not make good progress on switching from the existing power grid system to renewable power. Okay, so you're, and also when I was talking about a range of estimates for the public health costs associated with emissions, this is using a bad one for the power generation. So that's what's going on. And I'll encourage you to go ahead and look up the paper and take a look. that reflects the fact that there's a lot of control technology associated with conventional vehicles in terms of emissions. There's less so on kind of a lot of power plants that exist. Okay, we've cleaned up conventional vehicles quite a bit for the conventional air emissions relative to, say, coal-fired power plants. Right? Other questions? Yeah.
Suggesting that the new battery types have sort of solved the environmental problem of batteries since they don't have lead in them. And I'm wondering if you have any analysis of the heavy metal toxicity of the newer types of batteries or the recyclability of those.
Recyclability is an issue. To my knowledge, there is not a commercial operation for recycling lithium batteries. We happen to have a nickel cadmium recycling facility right near Pittsburgh, and so I went up and asked them what they do if they get lithium batteries kind of turned in their stream of nickel cadmiums coming in, and they told me they send them to landfill. Okay. The heavy metal content of a lot of the new batteries, and it depends on the battery chemistry, there's a whole bunch of battery chemistries, is much lower than, of course, the lead acid batteries. So you've got less of a problem there. What you do worry about is that the manufacturing of these batteries is fairly complex. And so there's a lot of energy that goes into that. There are rare earths, there are all these other things. Cause environmental impact and cause costs. So, but the end of life of lithium batteries is probably an issue for the next decade, because it'd be nice to get a channel of trying to figure out what might be recovered. In particular, rare earths are getting expensive enough. We're going to start trying to recover those from a lot of goods that are coming back that use them. A lot of recycling is driven by economics, of course, as my nickel cadmium recycler. They make money out of nickel cadmium, but can't see a way to make money out of lithium.
Yeah, I have a question. I guess most of the studies are based on the usage of electric vehicles of cars, or generally speaking, passenger vehicles. Then what about trucks? I mean, has the battery already been used, or is it possible to use them in trucks?
The Federal Railway Administration has sponsored the experimentation of a battery-powered locomotive. If you can do a battery-powered locomotive, you can do a truck. The only issue, of course, is what range you're going to build in for the truck. The electric locomotive that I'm talking about is not one that runs on a mainline track. It's a switching engine. So you can run it for switching for a shift and then recharge it. And it doesn't travel very far. The competing fuel that I didn't talk about, which I think may be of real interest for trucks going forward, may be natural gas. Natural gas prices are low. They look like they may stay low for a while. And in the same way they're talking about charging stations along interstates, it won't surprise me if it might become economic to put in compressed natural gas stations along interstates and look to run heavy-duty trucks on natural gas. We'll see. Interesting competition now going on among all the different alternative fuels that exist. Yeah.
Electricity has lower energy density than gasoline. But my understanding is that electric vehicles are more efficient in the way they move you forward. So do you believe that there is a way of compensating for that lower density due to efficiencies?
Future, potentially. Yeah, yeah. Well, I was talking about how I don't think the current generation of electric vehicles are optimized in terms of their battery management or the whole system-wide impacts of how they're working. So I see some real improvements possible there. I don't know when we'll see them in the production vehicles. I mean, people who have been working on battery technologies like crazy right now, and now we're just trying to catch up on things like degradation models. Because there's this trade-off between how you operate the battery and then what that impact is on the lifetime. And so you don't want to degrade the lifetime and then have to go through a battery replacement cycle before the end of lifetime for the vehicle itself. So all those are really interesting questions, and I think and good research questions for all the people in the audience.
But what about reusability? After 10 years of a battery no longer being good enough to move you forward, maybe those could be packed and actually used to put away electricity from renewables and find an afterlife for those batteries before they get recycled.
I mean, if you've got some reuse available in the batteries, there's clearly some backup power opportunities. There are people who've talked about using them as surge for wind, things like this backup. The difficulty there, of course, is that it's 10-year-old technology by the time it appears. And so I don't know what the battery technology is going to be like at that point and whether it will be competitive as you know, an old technology versus new technologies. I don't know.
Life cycle emission studies for other pollutants more commonly coming out of tailpipes?
There's been a heck of a lot of work on conventional vehicles and on a variety of different vehicles. There was a very nice review article that was done on this in Environmental Science and Technology this year by a fellow by the name of Troy Hawkins, who is a former student of mine, but he did a really good job. He works for the EPA right now. So I'd encourage you to, it's a review article, and it looks at like, it was something like 36 studies on life cycle of motor vehicles. Other questions? Okay. Thank you very much.